Good evening, everyone, and welcome to Straight Science. Straight Science is an evening science presentation series put on by University of Alaska Fairbanks, UAF, Northwest Campus here in Nome, and also UAF Alaska Sea Grant, also here in Nome, and you're in the home office tonight. So UAF Northwest Campus and Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples of the Bering Strait region, which is the homeland and waters of the Inupiaq, Central Yupik, and St. Lawrence Island Yupik peoples. So tonight's talk, I love maps, so I'm pretty excited. I'm already slanted towards Mark Zimmermann, and Mark Zimmermann is our speaker tonight. He is a NOAA fisheries research biologist, and he is in a different time zone than us tonight. He's tuning in from Seattle. He is with the NOAA Alaska Fisheries Science Center in Seattle. And I don't think you get much more straight sciencey than talking about the actual bottom of the Bering Strait. So hats off, Mark. This is probably the most straight science talk you could give. And for me, I'm excited. It's a very different, it's going to be interesting perspective, because for me, I look at it as we're finally going to get a peek at what the animals in our region and the U.S. Navy that are passing up and down the strait, what they already know. So we're kind of catching up to speed. And I want to thank Mark for tonight staying up late and bringing us this information. So with that, Mark, I would say take it away. Sounds like questions will be, he's got breaks in the presentation for questions, so we'll just see what happens next. Take it away, Mark Zimmermann, and we're so glad you're here.
Well, thank you so much, Gay. I really appreciate the invitation, and it's a privilege to be here and share some of our research with you. As Gay said, I'll be talking about a new map that we published earlier this year of the eastern portion of the Bering Strait. And this is a project that I did with Rebecca Woodgate. She's an oceanographer at the University of Washington's Applied Physics Lab, also here in Seattle, and Megan Prescott, who was my mapping partner at the Alaska Fisheries Science Center for 8 years. And before I get to this topic, I wanted to touch on some background information to try to put this more into a frame of reference for you. And to start, I wanted to show the maps that Megan and I have been publishing over the last several years. These maps cover about half of the Alaska EEZ. Each one is shown with its own color scale, with hot colors like red for shallow waters, and cold colors like blue and black for the deepest waters. Each of these maps takes at least one person year, or about 2,000 hours to make. One map that I focused on was the Central Gulf of Alaska, and I spent about 3,000 hours on that map. And Megan specialized on the Aleutians map, and together we have about 8,000 hours to make this Aleutians map, most of that time being Megan's. The last year we published a very narrow map along the Beaufort Sea coast, and we looked at the erosion and deposition patterns near shore, and we worked with the U.S. Geological Survey, University of Alaska Fairbanks, and University of Texas El Paso to compare what we saw underwater to what USGS had already documented on land with the dramatic erosion and deposition patterns that have been published there. And then earlier this year, in July, we published this very tiny map of the eastern channel of the Bering Strait, which borders our previously published Norton Sound and Eastern Bering Sea slope map. And we'll be looking at this area later. I know you can't see a lot of the detail in these maps, but you have to trust me, there is when you zoom in, and each map is many, many data sets, very carefully cleaned and edited and quilted together to make a continuous surface without seams. And to illustrate what I'm talking about, I have a demonstration map from around this tiny island called Middleton Island in the Central Gulf of Alaska. So when you go to the online sources that host the seafloor mapping data that Megan and I have used and download it and make a map, it often doesn't look that good. You get some strange artifacts, these bumps, these weird lines. There are groups of lines running east and west and north and south. Overall, it just looks very fuzzy and unpolished. But after you go through the process that Megan and I do, proofing and editing the data and stitching it together very carefully, you get a very different picture. You get a much smoother, cleaner picture. So for example, north of Middleton Island, there's this very distinct bank of shallower water, whereas in the unedited data, it's very hard to see. Coming off of that bank is a squiggly line going to the left. I think that's an earthquake fault or a series of faults. And that's almost impossible to see in the unedited data. Down at the south and west of Middleton Island are these lines radiating out like rays in a fish fin. You can't see those in the unedited version. To the east of Middleton Island is this wide band of smooth seafloor. And again, that's really obscured in the unedited data. And there's this big bump here in the unedited data, and that's just a wayward data point that we deleted. It's not a real seafloor feature. So we spend a lot of effort going from the unedited to the edited, and I'm going to give you more information about that. So to start with, I was going to give you some background about myself and tell you about where I work and my work organization. I know Dwayne Stevenson from my office gave a talk here last month. We work at the same place, so that might help as a frame of reference for both of us. And then I'll talk about the bathymetry or water depth data that Megan Prescott and I have worked with, and these old maps called smooth sheets that we've come to know and love. And then finally, I'll show you how we applied that for making this map of the eastern Bering Strait. When I tell people that I make maps, that I work in GIS or geographic information systems, the reaction I often get is that I must have an excellent sense of direction. And that is completely wrong. I have a terrible sense of direction. I'm always getting lost. And I was always getting lost as a kid. So I had to carry my favorite map with me. And that's this accordion thing in the background. And I've got it here, if you can see the picture. It's just falling apart. It's in tatters. But as a kid, hiking the trails and fishing at lakes in Yosemite, I carried it with me, and I would bring it out whenever I got into trouble and unfold it and try to find my way in the 3D world in comparison to the 2D world of the map. And I just think in terms of maps, and that's how I organize data. And I'm surprised when other people use equations or lines of code or flowcharts. That's not how I think. I think in terms of maps. And that is sort of how I ended up being a kid, hiking trout trails in Yosemite and catching eastern brook trout and brown trout, to conducting fisheries research places in far-flung places like the Aleutian Islands and catching much larger fish like this Pacific cod, although I think arguably much less attractive than the brownies and brookies from my youth. Opening up that map, this is the northeast corner of Yosemite National Park. This is some of the high country. The blue are lakes where we'd go fishing. The green are the forests, and the white or clear areas are the unforested, the granite, like here. A lot of this is glacially sculpted granite. It's just stunning. This is the map I carried with me, and you can see these holes in it. It's just falling apart. It's just in pieces. But to illustrate some of the elements of this map, which I apply to the seafloor today, let's take a look at Young Lakes here. This black line is the trail to get to the lakes. So the similar thing would be the path of the vessel I'm on doing a research cruise, or the path of a net being dragged on the seafloor to scoop up the fish for us to count. The blue lines are streams and rivers that connect to the lakes. collectively, they define each watershed, and that's another concept I use on the seafloor. These brown lines are constant elevations, and this 10,000 means it's at 10,000 feet. And we learned quite quickly not to go up or downhill whenever it was absolutely necessary because it was so exhausting with the thin air up there. Sometimes the trail would cross a line of elevation needlessly. We would go up and then back down again. And my dad would call these unnecessary hills because it was a lot of extra work to go up and down. And that makes me think of viewing that hill in a profile to see what it would look like in terms of a bump. So those are some of the elements that I remember from my childhood that I apply to the seafloor and how I got started with maps. So that's enough about me. And unless there are any questions about our secret trout fishing spots, I will proceed to the next section. So Gay told me you guys were very excited about organizational charts. So I have some to run you through to try to clear up any confusion about where it is I work. So this is the organization chart for NOAA, the National Oceanic and Atmospheric Administration. NOAA employs a staff of about 12,000 people. All the names and titles you see here are our leadership in the Washington, D.C. area. We're led by Dr. Rick Spinrad. At the bottom are what are called the line offices. These are the major divisions and the major topics that we work on. Starting on the right is the Office of Marine and Aviation Operations. These are the people who run the NOAA white boats like the Oscar Dyson and the airplanes like those Hurricane Hunter airplanes. Next to them is the Weather Service. You all are very familiar with the Weather Service. This is the largest line office with 4,200 people. Next to them is Ocean and Atmospheric Research. And then NESDIS, the National Environmental Satellite Data and Information Service. They host a lot of data that other parts of NOAA collects. Next to them is the National Ocean Service. They are the ones who conduct the surveys of the seafloor and create or update the navigational charts that we use. Well, after they collect their data, they send it to NESDIS for hosting. And then I'm in NIMS, the National Marine Fisheries Service, led by Janet Coit. We are the second largest line office at 4,000 people, or roughly 1/3 of NOAA works in NIMS. And to get the National Ocean Service seafloor data, I go to NESDIS, their webpage. And if I didn't say it, NIMS is led by Janet Coit. She's our assistant administrator. So here is the organization chart for NIMS. We have about 4,000 people. We have 3 main divisions. The green are the regulatory, or I call them policy programs. These mostly consist of the regional offices. And the one you might be familiar with is the Alaska Regional Office, run by John Kurland in Juneau. Operations keeps the gears of our bureaucracy running. And the purple is the science portion, and that's where I am. The science portion is mostly consisting of the Fisheries Science Center, which are scattered around the coast of the country. And mine is the Alaska Fisheries Science Center, which is led by Bob Foy. He has offices both in Juneau and Seattle. And previously he had worked at our Kodiak office. So the Alaska Fisheries Science Center is the largest science center and the largest office outside of headquarters. We have a staff of about 300 to 400 people, depending on how you want to count them. So we are roughly 10% of the National Marine Fisheries Service. Major divisions for us include fisheries monitoring. This is the group that counts the catch of the commercial fishing industry and also the bycatch. Lock Bay Laboratories are in Juneau. Our mammals folks research mammals from pole to pole. My division works closely with REFM, the Resource Ecology and Fisheries Management Division. They conduct age and growth studies, socioeconomic analyses, and they write the stock assessments. My division is RACE, and that's also where Dwayne Stevenson works. We are the Resource Assessment and Conservation Engineering Division, And we are the group that conduct independent fishery surveys. We do a lot of research out in the ocean. And when I say independent, I mean that we are independent of the commercial fishing operations that are monitored by the FMA division. Within RACE, I'm in the groundfish assessment program. We have a staff of about 30 people. And my office is in Seattle. I'm at the Alaska Fisheries Science Center. We're just down the road from the Northwest Fisheries Science Center, and we split off from them decades ago. We used to be one center. Other science centers are in California, Hawaii, Florida, and Massachusetts. And it was Washington State Senator Warren Magnuson that defined our mission in the 70s. He wrote and passed through Congress the Fishery Conservation and Management Act of 1976. He got us the property for our campus, the money for our buildings, and our staff. His legislation enacted the 200-mile limit. He set the path for Americanizing what were largely foreign fisheries. He created the fishery management councils, and he defined sustainable harvesting by doing such things as conducting surveys, like our groups do, recording the commercial catch, like the Fisheries Management and Analysis Division does, reducing bycatch, and protecting habitat such that the species can reproduce themselves. And this later became known as essential fish habitat. When his act came up for reauthorization, a young senator from Alaska named Ted Stevens offered to co-author it with him. And henceforth, it became known as the Magnuson-Stevens Act, or MSA. And that's been reauthorized several times, and it's up for reauthorization now. This is an aerial view of Sand Point. This is a peninsula of Seattle sticking out into Lake Washington. This is the campus that Senator Magnuson got for us, and that's where my office is. The rest of this is now city property, and it's known as Magnuson Park. About 100 years ago, this entire peninsula was a U.S. Navy air base. And their claim to fame is they took these rickety biplanes, a squadron of them, and they flew around the world successfully. And this had never been done before. They took this crazy circuitous water route because A, there weren't that many airports and they couldn't support airplane flights, and B, because they had float planes. Let's see. Part of the legacy of that air base are these enormous airplane hangars. We have 2 of them, and we use just the north half of this one for our net shed. It's where we build and repair our nets. And for comparison, this is a rugby pitch here and a soccer field here. So each of these is about the size of a soccer field. These nets are our sampling devices. We drop these on the seafloor for 15 minutes and scoop up the fish and identify them and count them. And that's how we get our population estimates. When you build such structures in our area, you're required to spend 1% for the arts. And we have several art installations, including a sound garden, which is a kinetic sculpture. It has pipes like flutes and weather vanes. And when the wind blows hard, you steer into the wind, and each creates a very eerie tone. And if that Soundgarden name sounds familiar, it should be, because that's where the Seattle grunge group Soundgarden got their name. And I should probably point out that NOAA, NIMS, and the AFSC are not officially related to Soundgarden, the band. Aside from our office in Seattle, we also have facilities in Newport, Oregon, Little Port Walter, Alaska, Juneau, Anchorage, Kodiak, St. Paul, and Dutch Harbor. The Newport facility is named after Senator Hatfield. The Juneau facility is named after Senator Stevens. And the Kodiak lab is just known as the Kodiak lab. Collectively, the Groundfish Assessment Program surveys hundreds of stations, and we blanket a lot of the Alaska EEZ with our nets to get an idea of how those commercially harvested stocks are doing. My group, the Gulf Aleutians Group, conducts the Gulf Survey stations shown as red dots. In odd number years, like this year, and in even number years, we go to the Aleutians, like next year. The Bering Sea Group conducts the Bering Sea Shelf Survey every year. They used to do a deeper water survey, but we haven't done that one in a while. And then occasionally they're doing Northern Bering Sea and Chukchi Sea surveys. And over the years, I've done about 50 cruises, and I can say I have fished at or near every red dot in the Gulf out to the Aleutians, every blue dot in the Aleutians out to Stalemate Bank and the Russian border. I've done the Bering Sea Slope Survey all the way up to the Russian border and just the central part of the Bering Sea. And I've never been north of St. Matthew and Nunivak. So I've never actually been to the Bering Strait. We have never used the NOAA white boats for our surveys. We've always chartered fishing boats, and this is a practice that goes back to the 1940s. And here's one of our chartered vessels with one of our orange nets on it. And it's from doing these surveys that I learned how depth or bathymetry is the most important predictor of fish distribution and abundance. And that's how I got to fall down this rabbit hole and study bathymetry so much. One of my former colleagues, Mike Sigler, published a paper with all these lovely graphs of showing how different taxa on the Bering Sea slope, including skates, crab, sharks, flatfish, sponge, and coral, have significant relationships with depth. So each graph is for a different species. The bottom axis is increasing depth from left to right, and the left axis is increasing abundance from bottom to top. The black line is the trend line, and then the gray area is the error estimate around that trend line. So for sleeper shark, they're quite rare in shallow waters. They have their highest abundance in mid-depth, and then moderate abundance in deeper water. For Pacific cod, it's just the opposite. They're most abundant in the shallowest of waters, and then they're basically absent in the moderate and deepest waters. And I know these names might not mean that much to you, so I have pictures for a lot of these. And starting in the upper left is a skate. Here's a Pacific halibut, arrowtooth flounder, grenadier, eelpout, sponge, slender sea whip, which is a type of coral, real coral, tanner crab, Pacific cod, and short spine thorny head. So all these different taxa, bathymetry and depth derivatives are the most important descriptor. And that's why I got into bathymetry. So I can pause there in case there are any questions about that portion of my talk before I get into bathymetry.
Any questions for Mark? I want to say thank you for the detailed organizational charts. That is that helped clear up for me a lot of the how that works. Thank you.
Oh, good. You're welcome.
Yeah.
Okay, so I'll plunge into bathymetry, which is the study of water depth, and talk about these old maps that Megan and I used called smooth sheets. So the National Ocean Service and Precursor Agency have been conducting hydrographic surveys in Alaska for more than a century. And these surveys result in these maps called smooth sheets, which were paper, and they were digitized some decades ago and are now available online. So Megan and I have been accessing these data sets and proofing and editing them. And in the process, we've learned a lot about latitude and longitude positioning, a lot about the tide, and a lot about the depth errors that we encounter and how to fix them. When I got into this, I was really scared that this was going to be a high-tech endeavor and I was going to get lost really quickly. But I soon realized that this was a retro project, and I had to learn about things like lead lines, which is how they used to measure depths. This is literally a rope with a lead weight attached to the end of it. Someone would be off the side of a ship and they'd swing it around. This is the lead. They'd let it go and sink to the bottom and then see what color ribbon the line went out to. And that's how they determined the depth. In the days before GPS and radio beacons, they used visual navigation. They would build towers on the shore on top of known locations. And then the hydrographers in the bay would use what are called hydrographic sextants to triangulate on these towers, and they could later translate those, use trigonometry to change that into latitudes and longitudes. As I said, originally the depths were taken with lead lines, and this shows how they would only be an occasional depth along the path of a vessel, not that much data. Starting in the 1930s, they invented something called a fathometer, which we now call a single beam echo sounder, and placed that on the bottom of the boat. This is just a unit that would send out a flurry of sound waves that would go down to the seafloor and then come back. And by measuring the time, they could figure out the depth. And if you hit the record button, you would get a near continuous set of depths along the vessel path, but it's still quite limited. You're just getting one data point per second or so. More recently, they learned how to arrange 100 or perhaps 200 or more of these single beam units into a fan-like shape. And these are called multi-beam units. And they give you a much wider swath than the vessel and allow you to map great chunks of seafloor. And in this example, they're showing that there was a mountain range here in the middle of these other transects, which the old technology wasn't showing you. So when we get multi-beam data, we use it, but we have often used single beam and lead line data too to make our maps. We always have relied on the low resolution navigational charts for creating and executing our surveys. These are great for navigation. In fact, they're mandatory for navigation, but they're quite poor for bathymetry. This example chart is of tiny little Kiliuta Bay on the south side of Kodiak Island. The chart is at a scale of 1 to 80,000, which is not that bad. But if you look in the bay itself, you see just a few numbers surrounded by large white areas. Each number is a depth, and there are some indications of substrate type, like here is an S for sand, but there are very few of those. Mostly it's just white space, and they just were giving you the highs and lows, and that's sufficient for navigation in the bay, but they're missing a lot of information to describe the seafloor. What I found is that this bay was originally surveyed in 1931 at a scale of 1 to 20,000, which is much better than 1 to 80,000. In that survey from 1931, they collected 7,500 soundings, but only 255 are on the navigational chart. They also collected 313 substrate observations, or information about the type of seafloor, but only 18 of those made it to the navigational chart. So what I found is that just a tiny percentage of the old data made it onto the chart. They only took 3% of the soundings, leaving 97% behind. So I wanted this. This was a treasure trove of data. I needed to work with this and learn how. And it was a difficult path. But when I told people what I was doing, they were very skeptical. And they didn't want anything to do with data from 1931. They wanted the sparse data from 1990. And I had to tell them, there is no data from 1990. This bay was only surveyed once in 1931. Each depth sounding here is from 1931. It's just been reproduced again and again. Okay, defer that with each edition. And it will stay the same until it gets resurveyed. So people find that quite surprising. The charts get reissued, yes, with new dates periodically, yes, but the seafloor stays the same unless it's been resurveyed. To get this data, this older data, I have to go to a NESDIS webpage, and this is at NCEEI, National Centers for Environmental Information at NESDIS. You use their map interface to pan and zoom to your location and find your little bay. This is Kilyuta Bay. You click on it and you get this window, which gives you access to their data that they have for it, and you can download it. Also notice that there is an outline of a survey right outside of Kilyuta Bay. That's another survey, and another one here, and another one next to that, and another one next to that. There are all sorts of surveys in this part of Kodiak with just a few blank areas that have yet to be surveyed. And actually, I found out by comparing the chart to those older surveys, there are 19 of these old smooth sheets, each with thousands or at least hundreds of soundings that I could use instead of the navigational chart. So that's what I wanted to do. There is unfortunately very little information about how these older data sets were digitized. There's one document written from someone from the US Geological Survey that talks about the Asheville project, where they manually digitized over 3,000 of these surveys and made them available online. And this is the process that they used to do it. They would get the paper smooth sheet or map out of the archives, place it on a scanner, and create a digital file. And this would be just like a picture you take from your phone. So it's like a JPEG or a TIFF. Then you bring it into a mapping program. You click along the edges where you see lines of latitude and longitude intersecting, and then type in those values. And that is a process called georeferencing or georegistration. When you do that, the map shows up in the correct place in the world in your mapping program. Then you can zoom in to the water and find those numbers that represent the soundings and click on each one and type it in. And that gives you the digital depth soundings. But for reasons that aren't really clear, they did all this work, but no one ever proofed what got digitized in comparison to what was on the map to start with. And these intermediary steps were not saved or were discarded, so they're not available to examine. So Megan and I have spent a lot of our time recreating these steps to georeference and compare the digital version of the soundings to the original chart. And we had to do this because I started noticing odd things. Like when I plotted out the depth soundings shown here in green for part of Kilyuta Bay, some of them plotted on the land instead of on the water. It seemed like everything needed to be shifted a couple hundred meters to the northeast, which was odd. And if you zoom out, there's a depth sounding 40 kilometers west of Kilyuta Bay. It's just an outlier. Someone made a mistake when they clicked, so that needed to be deleted also. At the edge of Kilyuta Bay, where there was an adjoining survey, the hydrographers wrote in red ink a few soundings from the neighboring survey just to demonstrate continuity of depths. But unfortunately, these got digitized twice, each with a slight offset, and this creates a stair step or seafloor feature. So we had to delete those extra soundings too. And then there were instances of where that lead line rope was too short. They were trying to measure this depth with a lead line that was 10 fathoms long, and they didn't hit bottom. So they wrote this symbol indicating it was deeper than 10 fathoms here, but they didn't know the depth. These got digitized as if that was 10 fathoms. So we were deleting these values too. And then there were just the standard typos like anyone would make when they're typing in data. This depth was 4/6 of a fathom deep, which is 4 feet. It got entered in as 46, which is much, much deeper than anything in this area. So we would fix that by comparing the number to what was on the chart. This was a totally new subject for me. I knew nothing about smooth sheets or hydrography. I had to ask a lot of questions from a lot of people and do some fast learning. And eventually I became able to read the smooth sheet. And there's different information or example in all of these boxes that are really important to be able to understand if you want to use this data, including information about the units of depth that they used, the tide information, and the latitude and longitude positioning information. And to start with, I'm going to zoom in on this little part outside of Shearwater Bay and show you examples of what they drew on this map. So this clear area is the land, this black line is the shoreline, and this area with the numbers is the water. These are depth soundings in fathoms. Each fathom is 6 feet, and these are all adjusted to mean lower low water. And they would measure the tide while they were collecting these depths and then adjust their soundings deeper or shallower according to the tidal cycle. This line is the shoreline, and it's also defined by the tide, but this is the high tide. Over here are some cartographic features. These branchy waving lines are kelp beds, and these were areas that were too thick with kelp for the hydrographers to go in and get a depth. This amoeba-shaped thing is a rocky reef. These plus signs are individual rocks that are always submerged. Asterisks are rocks that are sometimes not submerged. And then these tiny circles are little islands called islets. Over on the right are letters indicating different sediment types or substrate. So there's an M for mud and an STK for sticky. And yes, that's a legitimate sediment type. And then back on the left, there's this red triangle drawn on top of one of these tiny islets. And that's where one of their triangulation stations was. And this one has a name of Locks, and it was created in 1931. So these elements point to two different reference systems, a horizontal datum or reference system of latitude and longitude, and then a vertical or up and down reference system of the tides. If you have ever used a GPS or global positioning unit, you are using this horizontal reference system of WGS 84 or World Geodetic Survey of 1984. That's essentially a global system telling you how far west you are in terms of longitude from Greenwich, England, which is 0 longitude, and how far north you are of the equator, which is 0 latitude. That's a global referencing system. NAD 83, or the North American Datum of 1983, is a continental system, and that's what the National Ocean Service uses for their navigational charts. These are relatively modern datums, and they've been made with very sophisticated equipment to figure out their positioning. But historically, there weren't datums covering large areas of Alaska, and when hydrographers went to remote places, they didn't actually know where they were. They had to figure it out and use equipment and paper and pencils and do their best. And when they did, they would create a local independent datum, something called like Valdez or Port Hobron or Unalaska. And these were not affiliated or connected to any other system. They were completely isolated. Over the years, these places got revisited and reevaluated with new positions. And the stations that they created, those triangulation stations, were updated. And you can get that file from this website and plot out all these triangulation stations in Alaska. And they'll have both the new position and often the old position, so you can see how it's changed over time. And then the tides, that's basically the water going up and down. They consider the low tide mean lower low water. We'll look at that. And then the high tide is the mean high water. So I don't know if any of you have ever seen these triangulation stations before, but there are a lot of them covering Alaska. There are 24,000 spread across the entire state. There's got to be one very close to you now if you live in Nome. And I found them to be everywhere except for the north side of Attu, Chirikoff Island, and this isn't showing any at St. Matthew. I know they're there, they just haven't been updated, so I think that's why there aren't red dots for them. These are brass discs embedded in cement, put into something solid like a boulder or bedrock, with a triangle in the middle and then a little dot inside the triangle. Those are triangulation stations, Each one has a very well-defined position in terms of latitude and longitude. So to georeference or georegister the digital file of these old maps, Megan and I would take our mouse and click along the edge of the map at places where latitude and longitude lines crossed, and then type in those values. And you have to do at least 6 in order to get a georegistration. Sometimes you have to do a lot more. After we did that, we would zoom into this area, which gives us the latitude and longitude positioning information. And here it is. This was in one of those older datums, the Valdez datum, and they give you very detailed information about the latitude and longitude of this one station named Left. If you look that station up now, in the modern positioning system of NAD 83, you get a slightly different position. Instead of a latitude of 57 degrees, 15 minutes, and 28.4 seconds, it's now at 36.1 seconds. So it is considered to be farther north now than it was measured a long time ago in 1928. Similarly, the longitude used to be 152, 56, and almost 47 seconds. Now it's only 29.5 seconds, meaning it is farther east than they thought it used to be. So that means that all the information from this map needs to be shifted 7.7 seconds north and 17.5 seconds east. So Megan and I would have to go back and adjust those values that we had typed in for our latitudes and longitudes. And when we did that, everything lined up perfectly most of the time. Sometimes we had to redo it. So here was that station that we based our shift on, and the test was to plot all of the modern stations and see if the new red triangles plotted on top of the old red triangles, and that was the test. So that's the horizontal positioning or horizontal datum part of this. To go back to our example area, the chart also has information about the units of depth, fathoms, and the tidal datum, mean lower low water. In this part of the world at Kodiak Island, there are 2 high tides each day. They are of unequal height, and 2 low tides each day, also of unequal height. To calculate their low tide, they would get rid of the higher low tide and take the average of the lower low tides, and that's mean lower low water. And they would always set that to 0. So the scale started at 0, and 0 defines mean lower low water. So that would be like this depth sounding here. To calculate the high tide, they took the average of all the high tides and called that mean high water, and that is how they defined the shoreline. So it took me a while, but I finally realized that this line wasn't just a black line, it was an elevation. It was 7.9 feet or 1.3 fathoms higher than 0, just like that tide chart showed us. That meant that I could go along here and click and create points on here and then annotate them with this elevation of mean high water and create an entirely new data set that was vertically consistent with the soundings in the bay. Then when I used these soundings with these shoreline points, I could interpolate a depth surface of the entire bay that would run right up to the shoreline and stop. So if I zoom back out, we've corrected the smooth sheet for that offset. We've shifted the soundings to match the smooth sheet. So now each dot is perfectly over each sounding. I could digitize the shoreline by very patiently clicking in and zooming in and clicking many thousands of times along here to create all these data points. And then I could interpolate between these data points and create a shore-to-shore depth surface. And this covers the entire bay and does not leak onto the land. Once I do that, now that I have my shore-to-shore map, I can compare this to other maps, such as this U.S. Geological Survey topographic map. This is just like my trails map from Yosemite. The water lines up quite well with it. You can see a little bit sneaking through here and a little disagreement here, but it's really quite good. And again, this is 1931 data. This also lines up quite well with satellite imagery. You can see a few gaps here and here where it disagrees, but in general, it's really quite good. But you have to do the shift first, and if you don't do that shift, you don't do the data proofing and editing, then these old data sets just don't work out well. Okay, so that's the bathymetry background. Are there any questions about that part?
Any questions for Mark?
Yes, this is Doug. I'll just chime in. I've used charts a few times, or many times over the course of my years here, but I never imagined it was so complicated putting those together. That's really enlightening, going over all those details. Thanks.
Well, you're welcome. And it sounds like it might have made sense. So, yay.
Yeah.
Well, good.
Okay, so finally get to the meat of the talk tonight, the Bering Strait, gateway to the Arctic. I had met Rebecca Woodgate, the oceanographer, at an Arctic conference in Seattle and learned about her measuring of the currents in this really important area. And I hope one day to create a detailed map of her study area for her. And that was how this project came about. I really knew nothing about the Bering Strait until I met Rebecca. It's really interesting. There are so many divisions and connections in this area. I just had never thought about it, but it is the only connection between the Pacific and Arctic oceans. That's huge. Back during the Ice Age, it used to be land. This was the heart of the Beringia land bridge. It's not far away from the 180 longitude line, and that means it's pretty close to the division between the Western and Eastern hemispheres. As you guys know, it contains the international date line and the border with Russia. It's just south of the Arctic Circle. On the Russian side, it contains the eastern point of continental Asia, Cape Dezhnev, and the westernmost point of continental America, that's Cape Prince of Wales. Cape Prince of Wales is also the northern end of the continental divide of the Americas. That's an imaginary line that runs all the way through Alaska, Canada, the lower 48, Mexico, Panama, through South America, down to Tierra del Fuego, and that divides Pacific drainages from Atlantic drainages. Cape Prince of Wales is also the western end of the continental divide of the Arctic, and that defines north flowing drainages from southern flowing drainages. So here's a look at the Bering Strait. Here's Cape Prince of Wales, right near the town of Wales, and this is where the continental divide is. This is Cape Prince of Wales Spit, Cape Prince of Wales Shoal. These green dots are the traditional locations of Rebecca's moorings. She used to have both on the eastern side, the US side, and the western side, the Russian side, but these have not been in use for a long time. The international border and the international date line run between the Diomede Islands. And actually, when they established these, they didn't know what the longitude was. So they just said, let's call it halfway. And whatever that is, that'll stick. And then over on the Russian side, there's Cape Dezhnev. Here's the Arctic Circle. The strait is just south of the Arctic Circle. And that 180 longitude line is over here running through Wrangel Island. So it's really not that far from the border of the Eastern and Western hemispheres. So I didn't know any of this when I got started. This is just an amazing place. Here's another view of the Bering Strait, showing just how small of a connection it is between the gigantic Pacific Ocean and the much smaller Arctic Ocean. The strait has only been roughly estimated in size at between 2.5 and 4.2 kilometers squared. And Rebecca had, by hand, used navigational charts and given the whole strait an estimate of 2.6 kilometers squared, or 1 kilometer for the West Channel and 1.6 kilometers squared for the Eastern Channel. And that's the focus of my talk tonight. The strait and the passes of the Aleutian Islands and Shelikof Strait are really important for biologists like myself and oceanographers like Rebecca because they limit the flow of water. I've attempted to try to reproduce the major currents of this area, and the most important one for this talk is the red one. This is the Alaska Coastal Current, or ACC. This brings warmer, fresher water from way down south. No one seems to quite know where, maybe British Columbia or Washington State. This warmer, fresher water clings to the coast of the Gulf of Alaska, goes through Shelikof Strait, along the peninsula, and then most of it goes out the Aleutians. But in just the easternmost passes of the Aleutian Islands, a branch of it turned northward. And there it changes its name from Alaska to Alaskan Coastal Current, which I know is very confusing, but it's still the ACC. Goes into and out of Bristol Bay, crosses the Bering Sea, goes through the strait, into the Chukchi Sea, and into the Arctic. And there, just this current alone brings 1/3 of the heat flux and 1/4 of the freshwater flux to the Arctic. And that's a lot. And that's what Rebecca's work has shown, is how important this current is. Here are some figures that might help explain the oceanography of the strait. This is a profile view of the height of the Pacific Ocean, the Bering and Chukchi Sea, and then the Arctic Ocean. And this shows that, according to their calculations, the Pacific Ocean is actually taller in elevation than the Arctic, and it's taller by about 1/2 meter. So going from the south to the north, the main flow or through flow actually runs downhill. Water runs downhill into the Arctic. And these are figures from Rebecca. She took this picture out to sea. Looks like it was on the Alpha Helix. And she showed, you can see the ACC, or that Alaskan Coastal Current, as this gray slick in the distance. It is both warmer and fresher than water right next to it. And it's like a river. It's moving northward here at 2 knots. It's bringing all that warmer and fresher water into the Arctic. And here's a satellite image from a different paper that Rebecca wrote, showing how strong that current is coming through the strait. It's just ripping up the seafloor or the shoreline, and it's suspending all the sediment way northward into the Chukchi Sea. So I'll talk about how I put the bathymetry together for the East Channel, how we used it to calculate the minimal cross-sectional openings, where I had overlap between older and newer bathymetry data. I'll show depth change over time, and then we'll look at some seafloor features. This background map is from William Dahl from 1880. On September 5th, he went from Cape Dezhnev on the Russian side over to the American side, collecting vertical temperature profiles as he went. And this is his temperature profile map showing the Russian side here with the ice. All this was ice here in early September. That's something we just don't see anymore today. And on that day, while it was 2.8 degrees Celsius on the surface on the Russian side, it was 6 degrees warmer on the US side. And that's because of this river of warm water. That's the ACC here. And I think this is the earliest depiction of the ACC. And at the time, it wasn't known what it was. Another interesting thing is that this transect that he ran, that's roughly where Rebecca puts her moorings still. And it's been 140 years. So this is a very messy figure, but this shows the different data sets that we used to construct the seafloor map of the Bering Strait. First, we had older data sets, and these are shown by single color dots. These brown dots were a survey done in 1968. These bright green dots are soundings from a 1950 survey. Purple dots are another 1950 survey, and the dark blue dots are another 1950 survey. These cover only the part of the East Channel near Cape Prince of Wales. This area in gray was also surveyed in 1960, but they had navigational problems on that survey, and the data was either never completed or thrown away. So I don't have any soundings for this area from that early era. The strait was revisited, started in 2010, and these black boxes show the outlines of multi-beam surveys that were done in 2010. This was done in 2010, and then this triangle was done with 2 different methods in 2015. So they cover all of the western portion, but not the area near the Cape. To make a shore-to-shore map, I used these modern multi-beam data sets because those are the best ones, but I also had to add these older data sets to complete the picture, and then digitizing the shoreline here at Cape Prince of Wales and here at Little Diomede Island. Later, I could use this overlap to compare 1950 to 2010 depths and see if there'd been any depth changes. So this is the first detailed shore-to-shore map of the Bering Strait. I used my mapping program to figure out the location of the smallest opening, and that is this black line traced here. This opening was 1.8 kilometers squared with a maximum depth of 54 meters, and this was about 10% larger than Rebecca's estimate of 1.6 kilometers squared. But this occurred about 5 to 10 kilometers south of her moorings. So I forced a second cross-section through the moorings, and that came out to be 2 kilometers squared, or about 20% bigger than Rebecca's estimate, with a much deeper maximum depth of 54 meters. So those are the minimal cross-sectional openings of the strait. All the literature I read has talked about how tiny the strait is, and I wondered if it was unusually tiny or if it was just average, because a lot of it is really quite deep. Most of it is 50 meters deep or deeper, and I think that's quite deep for something that's so narrow. So Megan and I had previously measured the minimal cross-sectional opening and depth of all the passes of the Aleutian Islands and Shelikof Strait. So we compared these new values to those previous values. And it turns out there's a really good predictive relationship between the maximum depth of one of these openings and the total area of the openings. Each black dot is a pass of the Aleutian Islands. This red triangle is Shelikof Strait. And you can draw a very nice line through here, which is a good predictive relationship. Those 2 new openings of the East Channel plot above the line, meaning that for a given maximum depth, the cross-sectional area is bigger than one would expect. And that's because I think the strait is nicely U-shaped and relatively uniformly deep rather than a V-shape where you just have a deep spot at the middle. So it's bigger than we expected. Now the fun part. Let's look at some seafloor features. I don't think any of these have been described anywhere, but they're quite plain as day in the map. First, there is an offshore bar. This is a hump of sediment that runs parallel to the spit. This is about 1 meter in height, and I know it's hard to see, but we'll take a closer look at it later. Just offshore of that is an area of small sediment waves. These are perpendicular to the spit. And then seaward of the shoal is an area of large sediment waves, and these are parallel to the shoal. These 3 features, I think, are caused by that ACC disturbing sediment and dumping it just north of the minimal opening. Farther offshore, in some of the deepest water, are 2 pairs of seafloor gouges. These are, again, in much deeper water. I don't think they're caused by currents and sediments. I'm really not sure how to explain them. And I know these 3 features are hard to see, so these black bars show cross sections. I drew through them, and we'll look at those graphs next. And then later, we'll get to the central feature, which runs roughly north to south. And I did not know what this was. This is also previously undescribed. To me, it looked like a riverbed. You're splitting around this shoal. All right, so first are the cross-sectional graphs. In the upper left is the offshore bar. This occurred in very shallow water. This was a depth of about 6 meters. And there's this hump about a meter tall, and I think it's being shoved into shallower and shallower water as part of the spit building process. The spit has these alternating bands of land and water, and I think this is the next one. The small sediment waves just offshore of it were in 13 meters of depth, and they were only about a half meter tall. But those large sediment waves farther offshore were in water deeper than 40 meters and much bigger. These are 2 to 4 meters in height. And then those seafloor gouges far offshore, those were only about a half a meter deep. For that area where I had older data from 1950 and newer data from 2010, I calculated the depth change. Hot colors like red show erosion, and cold colors like blue show deposition. This shows that most of the East Channel has hot colors. Every red dot here has gotten deeper by a meter or more, in some places 3.5 meters deeper. The seaward face of the shoal has also shown erosion, such that the shoal is getting shoved towards the spit here. The only significant deposition in the strait is in the very deepest area, where the currents must be much calmer, and there is deposition there greater than a meter. And there's very light deposition seaward and shoreward of the shoal. Now, if we zoom out to the full extent of this data set, we can get a better look at that central feature that I thought looked like a river. It actually runs to the northern edge of the data set. That's extending 70 kilometers into the Chukchi Sea, and it runs to the southern edge of the data set. So I was really puzzled about this, so I started doing some research, and I found that in the Chukchi Sea, geologists have found similar features. Back during the last ice age, all of this seafloor here was land. All this was land, and there was a gigantic glacier on the Brooks Range here. And this is when a lot of the world's water was locked up in these glaciers, and global sea levels were about 120 meters lower than they are now. It is thought that at one point, these glaciers rapidly melted, the water rushed downhill and made these great gouges in what is now seafloor. Over time, sediments filled these gouges in such that they're not visible at the surface anymore. Although this is a terrible seafloor map, you can't see anything in this. But they found it with sub-bottom profiling, which is a way to look like an X-ray through the surface. So we looked at our map with a geologist to see if we might have that feature here. Here's that little riverbed on this tiny data set. This is the East Channel of the Bering Strait. We're plotting it next to our Norton Sound map, which we had published previously, and the Eastern Bering Sea slope map. These white stippled areas are thought to be where glaciers were during the last ice age. This black line is the continental divide of the Americas. And then for the 3 large inlets on the north shore of Norton Sound, I outlined their drainages here in blue, in red, and then green. And with a little bit of imagination, you can imagine these glaciers melting, water flowing downhill, and following the path of these white dashed lines, creating potentially one paleo drainage here, a second one coming out of Golovnin, turning sharply along the shore, carving this deep channel in front of Nome, and then heading up to the strait. And then a third one coming out of Port Clarence. This is very short. So I wonder if this riverbed-like feature here is a paleo drainage. Don't know yet. So for this project, we determined that the minimal opening of the East Channel is 1.8 kilometers squared, or a little bit bigger than Rebecca had estimated previously. It's getting deeper by about a meter and getting a little wider. But Rebecca has pointed out that it's already 50 meters deep. So this 1 meter is actually just a 2% increase in depth. So not that big a deal in terms of oceanography. And maybe we found some paleo drainages. And this came out in July in oceanography, progress in oceanography. And if anyone wants a copy, just hit me up with an email and I'll send you one. And that's the end of my slides.
All right. Wow, is what I have to say. I've been learning the whole time. Thank you so much for such a thorough presentation, honestly. All right, so for the Straight Science audience, while you're thinking of your questions for Mark, this is the time to throw in a little love in the chat box for the speaker. It is never easy to be a public speaker at any time. You're sort of worried about your slides and this and that, and I think we all learned a lot tonight. So I know I've got questions, but we will take any that you all might have first. Any questions about, well, map making? I have just a profound now new realization that it's a lot of work, and how many maps that aren't redigitized by someone like yourself. What is the chance of error? You know, that kind of thing. That's what I was thinking about. Like if it hasn't been attacked by you, you know, or another group doing this sort of work, or hasn't been redone with the brand new equipment, how accurate is it really? But so all right, I see no questions in the chat yet. So my question, I'll start. My question is, you were only able to do the US portion, and it looks pretty pretty interesting. What about the western side of the Bering Strait? We all understand here in the Bering Strait region, it's really hard to get data and to communicate right now across the way, but is there any chance of that in the future?
I'm hoping so. I'm writing a grant proposal to get some Russian charts digitized. There is a 1 to 20,000 chart that covers Big Diomede Island, and I'm hoping there's some good data on that. There's also a 1 to 100,000 scale chart that covers the whole strait, and there may be some other soundings on there. But I really won't know until I get the funding and get the chart scanned and digitized what there is.
Can the US Navy help you at all there? They're not supposed to be collecting data on that side, but maybe before the world got tighter, maybe they were.
I don't know.
Okay,
I really
wait.
don't know. I don't have any contacts there right now.
All right. Well, I'm sure someone in the region could put you in touch with someone from the US Navy, actually. So we'll look into that.
Okay.
Question in the chat is, Mike Willis, are you able to speculate about any implications of the deepening you've observed through time? Would that indicate a greater amount of the freshwater influx from the coastal current you mentioned into the Arctic Ocean?
I would think so. This new bathymetry needs to get incorporated into oceanographic models, which look at a variety of things, including like friction of water moving along the seafloor. They're very complicated. And again, as Rebecca pointed out, yes, it has gotten deeper, but it was already pretty deep. So she didn't think it would make too much of a difference with their calculations. But I'm hoping to work more with modelers and to provide them with better and better maps and see if that changes their calculations.
All right. Thank you, he says. Very interesting. Thank you. Have you been able to, Mark, look at the Office of Coast Survey? I think that's what it's called. The NOAA Corps guys were in Port Clarence doing a really detailed map of the Port Clarence and also the Emmerich Basin and the little channel that goes between Teller and the north shore of Port Clarence. Have you had a look at those data? Because when you were describing that river that was coming, you know, in your thoughts from the glacier, that they showed us in Nome. I think they were at the campus here and they were showing us their, it's not, I don't think it's published. They were just showing us what they'd done in Port Clarence. Unbelievable, because right between the Teller, end of the Teller Spit, just across to the north shore of Port Clarence there, it's not very wide. And when they did their side scan sonar or whatever they had, it is a perfect, like a little U shape, as if there'd been a waterfall there. And it goes from something like 20 feet to 150 feet, boom, just like that, right where Teller, right in the Narrows there. And it is incredible. And they have incredible definition because they were using all their fancy new equipment in their small boats and all that. Have you been able to see those? Because I was like, wow, maybe that really was a giant waterfall back in the day.
I can't remember, but they post their data sets when they get them all finalized on that webpage that we go to. Then it takes somewhere about a year for them to finish it up and process it and get it posted. So I'll look again tomorrow and see if I've gotten those data or not. I can't remember right now.
Okay, but I mean, I think just for your curiosity, it would be really interesting for you to see it because it was so stunning.
Yeah.
Because when you look at it, it just looks like, oh, there's just a little Narrows there. There's a lot of marine and mammal activity. There's a lot of fish activity, bird activity right in that narrow area because you can imagine the currents are hitting that. It's like a straight wall and just curling all around. So very interesting. Or they're dropping as they're leaving the Emmerich Basin and getting the water going into Port Clarence. So very interesting. Oh, sorry, Grantley Harbor, not Emmerich Basin. Grantley Harbor for those from the Bering Strait region. Emmerich Basin's further up past Tixook Channel, which in itself, that would be very interesting as well. So that makes sense what you were saying about the glaciers. So the water then would be rolling, if we did have this glacier melt, that would be rolling, as you show it, northbound.
Yeah, I'm guessing. I'm really ignorant about this, but just following the lines there on the seafloor.
Right. All right. All right. Any other questions? Dean Stockwell, go ahead.
Yeah, hello, Mark. I have a lot of questions in a sense. I'm a biologist basically. So when I look at this, I see you're looking at a 55-mile area across the straits. In that 55-mile area, there are at least 5 different types of water units moving north at any one time at different velocities. You mentioned the Alaskan coastal current. You mentioned all of these other things. They're all traveling basically at different velocities. You mentioned the influx of fresh water increasing, but also at the same time, the increase of Pacific water through the straits is increased. All of these tend to modify the benthos, the bottom organisms. And I just get confused at times when I'm looking at kind of the biology and what this means to the biology. It's a complicated story. And yeah, I think you've made inroads, but I think there's a lot more there with sediment types because that's really important to the organisms that live in the bottom. And if that's changing, I mean, we've already seen a flux of fish moving north, large fish grazing on the benthos. I just wonder if you had any thoughts to the different velocities across the straits, not only, as related to the benthos.
For the movement of the water, I'd have to defer to Rebecca Woodgate about that. She knows all that stuff, and I do not. The modern multi-beam surveys did collect sediment observations throughout the east channel of the strait, and they found most of it was, I think, what they called pebbles or rocks, and it was largely clean of the finer sediments, except on the sides, like near the shoal and around Diomede Island, Little Diomede Island. So it's mostly rock.
Okay.
All right, thank you. And actually, Dean, thank you. That brings up a good point. Since you have your fish biology hat on for the moment right now, Mark, given that we have seen such a massive, or we are experiencing a rather ecosystem-wide transition of ecosystems as we are losing the thermal barrier ability to be strongly renewed. due to the loss of duration, extent, and quality of sea ice, being able to renew that barrier, and we have another ecosystem rolling northwards. Are you familiar with some of those race division results in the northern Bering Sea? The big switches of, we've got Pacific cod and we've got pollock and we have all these other things.
I've heard about them. I haven't read them that much. Dwayne Stevenson would be the expert there, or perhaps Lyle Britt.
Okay, I just kind of wondered when Dean was talking about sediment types, I was thinking, wow, I wonder if there's any, if it's changing the structure of the benthos, are there fish? And I was thinking of the fish that are coming in, or maybe the old guard fish that we used to have. Is that a better habitat for new fish species? Or maybe this question isn't, you're not able to answer this one. But
Yeah,
that
I'm not able
seems
to
part of
answer that.
fish aspect of it.
But I do think Rebecca has shown increasing movement of water north through the strait. And she has also shown how the water movement is dependent on the wind to a great extent. And the water flow northward can be stopped and it can be completely reversed by the strong winds. I see someone's in the waiting room.
Oh, thank you very much. Look, I missed him. He jumped.
Um,
Tom's iPhone. Don't know who that was. He'll come back if he wants in.
so Rebecca has shown that yes, there's more water moving northward, but it is highly dependent on the direction of the wind, which is something I never would have thought about.
Okay, yeah, it is very much driven by the wind, and right now we're getting a heck of a lot of north wind currently, so we're hoping that the ice is starting to drive down, which is nice for everybody. Doug, I see your hand up. Go ahead.
Yeah, this might be an unfair question for you there, Mark, but you might have some insights on this. But we hear a lot about the Gulf Stream, concerns about climate change at the Gulf Stream getting weaker and things. And you showed how the currents go through from up the eastern Pacific coast up into the Bering Sea. Are you aware of any discussions on how those currents could change with time because of climate change or increasing sea levels? You noted that it's a 0.5 meter difference between the Pacific Ocean and the Arctic Ocean. So any points insights on any of that?
That's well beyond my knowledge, but a very good question. I would say that in my discussions with Rebecca, she has emphasized how the ACC is a seasonal feature. It doesn't run all year, and it's fed by the runoff of the rains and snowmelt farther to the south. So if the runoff pattern changes, I am guessing that the ACC will also reflect those changes. But again, Rebecca would have far better insight on that than I do. I'm not an oceanographer.
Well, just knowing that it's seasonal, that gives some insight there too, compared to the Gulf Stream, which is not seasonal. But yeah, thanks.
All right, I think we're winding down. My last question is, you showed a picture of the Northern Bering Sea survey stations, the Southern Bering Sea stations for the benthic trawl, and you showed the Chukchi Sea stations. So I think it's been, I don't know when the last time the bottom trawl survey, have they done a Chukchi Sea survey?
I think they've done one
One.
in recent years. And I think there was one done maybe in the 50s.
Okay. I don't know the recent years, but it would be very interesting to hear what they found back in whenever that was. I don't think it was in the 2000s.
And there's an NPRB sponsored Arctic integrated ecosystem research program. And they've been doing surveys up there for, I don't know, the last 5 or 7 years. So they've been collecting data in that Chukchi area. I don't know if they've been using the same bottom trawls that we use or what their sampling equipment is.
Okay. It's probably different kind of equipment. But anyway, that I've got to track that down. That seems pretty interesting. That is part of our region. So into the Chukchi Sea. So with that, any other questions? I want to thank you, Mark. If you want to stay on after everybody goes just for a sec, that would be great. I know it's late for you, and we want to thank you again. Next week, we have for Straight Science, we have Hayo Aiken. He is the director of the UAF International Arctic Research Center in Fairbanks, and he's going to be talking about a sort of a long-term Arctic program study that's beginning called ROADS, and it's an acronym for something we'll learn about. And they're thinking of coming to the Bering Strait region. So we'll hear more about that program and his work as director of the International Arctic Research Center in Fairbanks, and thoughts they're thinking about for the Bering Strait region. With that, thank you again, Mark, and stay safe, everybody. It's a little chilly out there tonight, so take care, and we'll see you next week. Have a good night.